I think we can get started. Oh, wow. Okay. So before I start, I always like to do this, and particularly in this talk, but in all the data science talks that I give. How many of you are data scientists, would you say? Raise your hand. All right, lots of data scientists. How many of you manage data scientists or consume the output of data scientists? Brave souls. All right. So hopefully we'll have something for both of you. There's enough data scientists in here that I'm actually scared to accept your questions, so I'll leave as little time as possible for questions at the end. I'm joking. All right. So first we're going to talk about some preliminaries. I'm going to talk about data science a bit, and I'm going to talk about an idea that I haven't heard really talked about a lot, but I think is actually quite useful. It's borrowing from other domains, right? Then we'll look at a demo, and we'll take your questions. Okay, so my name's Casey Stella. I work at Hortonworks. I'm a data scientist in the engineering organization. I work on the Apache Metron project. Before that, I was in the consulting organization. So I was the guy who went around and did data science stuff for people, right? So companies would bring me in, I would either advise or actually write code. I wrote a lot of code. So I was a working data scientist. And this is what this talk actually came from. So before that, I worked in the oil industry, but most importantly, I worked at a healthcare startup in the US called Explorus. They recently got bought by a little company called IBM. They're part of Watson Health now. So we were doing a lot of clinical data analysis. So you're going to see that here. So specifically, the demo is going to be around the medical domain because we are very interested in the United States at fixing our healthcare issues because we have a lot of them, right? Before that, I was a graduate student in math and CS. So challenges of data science. So this is hopefully to build some empathy. I'm going to tell the data scientists what they already know, I hope, and hopefully to build some empathy with the managers. So data scientists really have a tough job, right? We have to merge analytical skills with domain expertise, and that can be tough. Right, I've worked in a lot of different domains. So just before this, medical, I did seismic data processing in the oil industry. I think I've hit pretty much everything except for finance. I've not done finance yet, so hopefully I can avoid that. No, I'm kidding. And a lot of times we're thrown into places where we don't have sufficient domain experience. Even if we do know about medical, like I came into Hortonworks knowing quite a lot about medical data from the hospital side, right? But then pretty much immediately I was thrown into an insurance company. An insurance company has a very different kind of view of medical data. So even within the same domain, the views of that data are quite different, right? They're either incomplete in some ways and not in others. And honestly, gaining this expertise can be quite time-consuming. And so generally what you do to gain this kind of expertise is you round together people and you talk to them, right? You gather together people who know the domain and you kind of pick their brain. Well, I found that that's really difficult in certain domains. In particular, in medical, I would have to like talk to doctors a lot. I don't know if you've ever talked to a doctor. How many people have talked? Everyone's talked to doctors who've been to a doctor, right? So doctors, and I love doctors, but they are extremely, what's the word, busy, exceptionally busy. And they do not want to answer dumb questions. As soon as you ask what you think is a dumb question to a lot of doctors, they just immediately like click on the bozo bit in their brain. They're like, nope, this guy, he's not going to be okay. So it was quite a challenge. So what I ended up doing is actually talking to nurses. Nurses know all about healthcare, it turns out. Like if you're changing bedpans, you know that stuff from the bottom up, man. All right. And also, a lot of the stuff that we were cared about in the insurance industry was, and it actually also in the hospital was around the stuff that nurses did, not necessarily the pure medicine stuff. But what data science really should do is to be able to kind of merge those two views together too, right? Where doctors are concerned with sort of the pure medicine, the diagnoses, and the nurses are concerned with a lot of the detail work, like what code is this? Does this person have heart disease, or does this person have heart disease with certain complications, right? Stuff like that. So, and the hope was, and what I found was that Unsupervised machine learning techniques are actually quite useful at understanding these complex data relationships. And we all know this, but we rarely apply them. When I go to data science talks, I looked around at the data science talks here, and everyone's talking about supervised learning. Right? Everyone thinks of, when they say data science, like, oh, machine learning classifiers. And deep machine learning classifiers, it's a new thing. And, but actually, most of the things that I need to do as a data science guy is scrub data and understand data. Those are my two main things. It's like 70% scrubbing and 70% understanding. No, I'm joking. But that scrubbing and understanding kind of overlap, right? I make that joke, but there is, like, you have to scrub the data to understand the data. And actually what I found was, by getting your hands dirty with the data, you start to understand the domain a lot more deeply than you do when you just talk to doctors, things like that, or domain expertise. So the other nice thing, actually the other thing about that is, when you go to talk to experts, when you talk to experts about their domain, they're coming with a biased view, right? Doctors have been trained exceptionally well, and they're going to know very deep things, but they're not going to know all of what the data is going to tell you. And oftentimes you find stuff that's unexpected. And honestly, that's what you're there for, right? That's what data scientists are there for. It's to find sort of the unexpected that's important, right? There's lots of unexpected things that are not important. The trick is finding the unexpected things that are important. Okay, so what we're going to do is we're going to borrow an unsupervised learning approach from NLP to look at non-textual data. So for the people who came in here expecting like an NLP talk, I apologize. I promise it was not a bait and switch on my, I don't think it's a bait and switch. I think you'll find it interesting, but it's the same technique. So in particular, the unsupervised learning technique that we're going to look at is Word2Vec. So I'm sure all the data scientists have heard of this. Anyone who's touched NLP has heard of this. And it's a vectorization model. So what a vectorization model is, so let's roll back here. So classically, when real statistical machine learning kind of hit the natural language processing stage, really the dominant approach to constructing vectors out of sentences, right, or documents, was what's called a bag of words model. So the bag of words model said, if I had the word "the" 5 times in the sentence, then there would be a particular column for "the," and that would be 5, right? And then it became more complicated, where they would do things like replace it with the TF-IDF or whatever, right? But the point here is, you're constructing vectors, which we know how to use easily, and there's lots of techniques using those vectors in NLP, but for doing other kinds of machine learning, right? But it's a bag of words. There's no notion of this word is near this word, or this word comes before this word, right? So what the guys at Google did was, they said, look, we're going to create an alternative vectorization model, right? And what this is going to do is, it's using deep learning, right, to construct what's called an embedding, right, a vector embedding for words. And what this is going to allow us to do is, it's going to allow us to do things like ask for similar words. So what are synonyms, right? What words are closer to one another? Like, if I have the Yangtze River is maybe close to the Mississippi River, and maybe it's far from cottage cheese, for instance, right? The other cool thing about it is, the other cool thing about it is, you can do things like ask analogies. So you can do things. So the classical example for Word2Vec is the vector representation of king minus the vector representation of male plus the vector representation of female is close to the vector representation for queen. That's kind of cool. So now you can do arithmetic on this. Bag of words model could not do that necessarily nearly as easily, or in any sort of principled way. So now I've gone from just having a bundle of vectors to having a vector space, right? Something that I can actually do linear algebra on. And linear algebra is tractable, and it's very computable, easily computable, not easily computable, computable. So now we're cooking with gas, right? They're using a neural network. But here's the problem. So I'm a working data scientist, so that means I have to go to the guys in management and explain what the hell I did. And if I say, well, I use this deep learning technique from Google and it's going to give me a word embedding, they're going to be like, what? Why would I trust this at all? Especially doctors. They do not trust your black box algorithms, not even a little bit. So pretty much everything has to be explainable, or at least have some sort of analog in either the physical world or in the world that they understand, right? And they really understand like counting quite well. They can count things. It's not a dig on doctors, but they count very well. So there's some work by some guys at Stanford that shows that the word-to-vec model is essentially equivalent to like a co-occurrence matrix with some window distancing and a factorization to project it to a lower dimension. But that meant that I can do things like say, it's like a word co-occurrence matrix. It counts the number of times that each of the pairs of words were near one another. And there's some magic that happens on the back end, but at the heart of it, it's what that is what the neural network is learning, right? And by the way, I would suggest that little link down there. If you're ever interested in making sense of word-to-vec, there's a really great blog post by the guy who did one of the Python libraries, Ginsem, who implements word-to-vec, and he really lays it apart. He really lays it bare of what's going on under the hood. It's really cool too. Okay, so what does this have to do with? What does it have to do with medical data, right? So everyone here's gone to the doctor. I assume you guys weren't like born outside of a hospital. Unless you were born outside of a hospital and never gone to the doctor. You have been inside of the medical system. So when you go to the medical system, you go to the doctor, you're sick. What the doctor does, and what the nurses do, they take your vitals, right? Your height, your weight, your BMI, especially in the United States, because we're fat. And they're very concerned about that. You take labs, you get some blood tests, make sure you don't have hepatitis, stuff like that. There are some procedures performed. So you broke your arm, you get a cast, you get an X-ray, that kind of thing. And diagnoses are made. I put an example there, diabetes, because we also have a lot of diabetes in the U.S. So this is a very U.S.-centric talk. And then at the end of the day, drugs are prescribed. But if you really think about it, what are sentences, right? This forms this kind of semi-structured, ordered, way about the way that this procedure happens naturally follows the kind of progression you have with sentences. Or with each of these type of things are kind of like a part of speech. Vitals, labs. Well, okay, labs are continuous variables, so what do? Well, you generally bin them, right? You say, okay, this is the 95th percentile of this particular lab. And the nice thing about medical data is they actually have all this stuff coded up in an ontology, right? So now I've transformed each of these things into words. So a particular instance, a particular encounter, and to use the vernacular of the domain, particular encounter is a linear progression of these instances or these words, right? Vitals are taken, and those are the results, right? The height is this, the weight is this. Labs are taken, and these are the results, right? Procedures are given. And so at the end of the day, we have a bunch of sentences, which are constructed out of clinical words, right? So clinical sentences or encounters are constructed out of clinical words. And that forms kind of that sort of vague semi-structure. If you think about English, English is a really complicated language, right? Where there's all sorts of different phrases can happen before other phrases and things like that. So word-to-vec is built to really unwind some of those nuances, right? So why is this useful? Because what's coming is we're going to use word-to-vec on these clinical sentences. And why is this useful? Well, if I'm building models, I need to understand how in my feature extraction phase. I was talking to the guy, Ram, from Google, who did the TensorFlow talk yesterday, and he's like, man, people don't realize like 70, 80% of everything is just feature extraction. If you get the wrong features, you're dead in the water. I don't care how great the algorithm is. I mean, to a certain extent, deep learning is like, well, we're going to figure out the features through this really, really, really deep network. But at the end of the day, for the working data scientist, if you want tractable results, you live and die by how well you can figure out what is associated to what. So I'm on the job, right, at an insurance company, and they're like, we want you to build a model to predict who has diabetes, or to predict who has a high BMI. Those are the kind of models. So they can figure out who it is and say, reach out to them and say, well, hey, you have diabetes, but we have not diagnosed you with diabetes. You should go to the doctor, right? Or we have miscoded you. We have not indicated that you have diabetes. Are you sure? So we'll contact your doctor, stuff like that. So that's generally the pipeline. But if you go in, like, I'm not a doctor. I don't know about exactly what, I know in general what happens with diabetes. So I'm sitting here reading Wikipedia entries, right? But the Wikipedia entries are written by people who studied in medical school. So they're coming at it from one perspective, and that's valuable, right? I know that blood glucose is associated with it, and I know that these various things are associated with it. That's this outcome, but the question is there anything hidden? Is there any really good feature outside of that? So we had to build something kind of like this using a different approach. But afterwards, I realized when I started looking at WordDevac, like, this is a really great idea, right? This is a really great way to do it. I wonder if it actually works. And I think it does. So what we're going to do is we're going to use WordDevac to build a model and build this vector space representation, this embedding, and use it to investigate where these, how these clinical words are associated with one another. So you can ask questions like, what diseases are closest to diabetes? What diseases are closest to, or what drugs are closest to diabetes, right? Okay. So the real problem here is the problem with any public talk or any data science is access to data. Like, that's our main concern. Whenever I'm brought into a client and they ask, is this possible? And I say, well, theoretically, if you have the right data, maybe, which is not an acceptable answer, which the people who raise their hand when I ask them if they manage data scientists will tell you. If they want to say, absolutely, and it'll be done in 2 weeks with high accuracy. But actually, as part of a Kaggle competition, this EHR, electronic medical records system called Practice Fusion, opened some depersonalized medical records, which is the ballsiest move I've ever seen of a company in my life, because this stuff is super, super, super sensitive. But it's depersonalized, right? But if you get that depersonalization wrong, you just released a bunch of people's medical records to the internet. So what we did, or what I did was, it was around 197,000 clinical sentences, so a small data set. So just to compare, we had literally billions of them in the insurance company, right? So this is small. So we processed it with Pig and Hive, and we got into these clinical sentences, right? We ingested it into Hive. We used Pig to kind of go through this and construct this unstructured, or this sentence representation. And then from there we use Spark. Spark has a nice WordDevac implementation built in since a ways back. And we built the embedding. And then we started looking at what the connections were. So if I'm building a model around atherosclerosis, I'll look at the codes for atherosclerosis and see what's connected to what. Okay, so I'll show you the end of the pipeline here. And this is a Jupyter notebook. I like to do things inside of Jupyter if I can. It's actually quite a little bit of code. We're building a 100-dimensional representation for the vector. So for the vector space, I tinkered around with others. This happened to be the best one given. So the challenge with doing this in other domains is you need to know something about the domain. So how do you choose the best representation? How do you know if it's a good representation? I get that question a lot. And here's how you do it. Presumably, you could recreate the things you already know. Hopefully the embedding will recreate the things that we already know about medical science, because we have been doing this for some time, right? So we know that atherosclerosis, or heart disease, is associated with peptic ulcers since like way back. Hopefully I'll be able to find a connection. Hopefully those will be close together. All right. And so we just fit the sentence. And from here, it's just a matter of being able to get the nice, so the medical codes, you really want like a textual description of the codes, not just like the code number, because most people don't know that stuff, and that's surprisingly difficult to do because of how the data is formatted. But so let's look at this. Let's look at the data. So I picked like the big diseases, and I want to see if it's reasonable. And I picked some small diseases that are maybe some small connections that maybe aren't as well known. All right. So atherosclerosis, the ICD-9 code, that's the coding system used. Actually, ICD-10 here in Europe, and actually ICD-10 back home. But at the time of this talk, with this data, it's ICD-9. That's a coding for diseases, right? For diagnoses. I'm really going to kind of focus on diagnoses. So we look at the we look at all of the close clinical words or clinical words that are diagnoses to atherosclerosis. So you can see right bubbled up at the top here are peptic ulcers, right? So this is a cosine similarity. So closer to 1, the closer to 1 it is, the closer the closer the vectors are together. So here's my beef against the Word2Vec implementation in Spark. I would like to be able to do this with alternative metrics, right? That works quite well for documents, but I might want to be able to do like an L1 or L2 or L infinity norm type of thing, right? But for here, this works fairly well to get to kind of in our feature extraction and data understanding phase. So we've known this connection for a while. There's a link to way back in the 1970s, the British Medical Journal was talking about this connection. Right? What might not be known, though, is this guy, which is quite strong. The sensorineural hearing loss. So hearing loss is associated with atherosclerosis. Right? So I thought, there's no way this is true, right? So I started looking. Sure enough, Journal of Atherosclerosis in 2012, very recently, found that hearing loss seemed to be associated with vascular endothelial dysfunction and increased cardiovascular risk, which is to say, heart disease, right? Unexpected, relatively new result, right? Classical result bubbles right to the top. The slightly less expected result bubbles up here. So that definitely, if I'm building a classifier around classifying who might have atherosclerosis, hearing loss becomes one of my features, right? But also, beyond that, if I'm a researcher and I'm looking for connections that I might not have known, this is a grab bag of things to try, right? They may not all be there. And then some of them, and you'll see this slightly later here, what this really is a correlation engine, not a causation engine. So just be very careful about it, right? We have a really bad track record around finding causal links in data science, right? It is a lot easier to find the correlative links, right? These are correlated. So for instance, moving on, knee joint replacements here. Another quite strong connection, 0.9, quite close to 1. Why is that the case? And it seems to be there's a solid connection between osteoarthritis and atherosclerosis in literature. And the belief is that this is correlated because of age, right? People who are older have heart disease. People who are older get knee replacements, right? So you see that is a correlation found. But correlations and causations can kind of be mixed together too. So be aware of that. So the other one I wanted to look at was Crohn's disease. This is kind of a nasty one, but a lot of people have it. It's an inflammatory bowel disease, and it's quite unpleasant. But a lot of people have it and live with this. Like entire life. It's quite bad. But there's not a lot of solid research about why this exists in the way that it exists. Like, what causes this? So I wanted to look at it. So the top length, the top connection is arthropathy, right? So arthritis, in effect. So if you look at the Crohn's and Colitis Foundation of America, the most common comorbidity or disease or diagnosis that is also present in patients with Crohn's disease is arthritis. And in fact, it's arthritis in young patients too. So it's not just the elderly who have that connection, right? But the one that I thought was really interesting and I did not find in the literature is this guy right here. This is a dental abscess. So that is not in the literature at all. However, if you go to the Crohn's disease internet forums, they talk about this all the time. This is a common complaint. In fact, the link that I have there, I believe, links to a discussion thread around a guy saying, look, I've had dental abscesses like 5 times in the last 6 months. What is going on? And just a bunch of people saying, don't worry, we think this has to do with Crohn's disease, but the doctors are saying it's not necessarily, right? It is a connection. It is an absolute connection, but has not made it to literature yet, right? So, and it makes sense if you think about it, right? Crohn's disease is a disease of the alimentary canal, your digestive system. The first point in the alimentary canal is your mouth, right? So if it's attacking other parts, it very well could be attacking all the way through. That being someone with no medical training, just having dug around in medical data for a long time. So I'm not your doctor nor your lawyer. The other nice thing about this one, or the other interesting thing about this one is this guy right here. Yeast infection on the skin. So there is the belief that from the Critical Review of Microbiology, very recently, I believe, oops, that's not what I wanted. From the Critical Review of Microbiology, there. That's not going to get better. At any rate, from the Critical Review of Microbiology, there was a recent paper, I think 2015, maybe 2014, suggesting that it might be our body's immune response to yeast infections that are causing some of this, some of the inflammatory bowel diseases, in particular Crohn's. Right. So it's a strong comorbidity. It's a strong correlation, is the idea. But also, what you want is beyond just diseases that are associated with other diseases. Right? You also want to be able to find like drugs that are associated with diseases. Like the common question that I had was, okay, what drugs do you use to prescribe? What drugs do you prescribe for, diabetes? And you'll get like the top 2 or 3 or 4, and you'll look around, and maybe you have to pay for like a website that'll tell you the disease, the drugs that are associated. But the data's all there. Like I know which drugs are being given, but the problem is, like Tylenol is given to everything, right? So it's not just a simple count. Right? You really want the unique drugs associated, and that's exactly what this gives you. So you can see the drugs associated with HIV. So this guy right here is the triple cocktail, which is very commonly used to help HIV patients. One story about a previous version of this guy that actually went into production with more data. Not necessarily this technique, but it was kind of an interesting story. We found that HIV patients were strongly associated with extra heavily fluoridated toothpaste, being prescribed heavily fluoridated toothpaste. It's because the triple cocktail ruins your teeth. So you need extra strong toothpaste to prevent your enamel from being eaten away, essentially. That also was not in the literature anywhere. It's sort of independent prescriptions by different doctors, right? not necessarily associated with HIV. But that again showed up in the HIV forums, not in the literature. Okay, so my pitch. These kind of unstructured techniques fit for a lot of different domains. Don't think this is just a medical thing. If you can fit, so I work in the Apache Metron project, which is a cybersecurity project. This absolutely fits in the same boat, right? You have actors that are doing this and then this and then this, and eventually there's an attack that happens, right? Finding the actions that are most connected with the attack is an important part of data understanding, right? Other kinds of domains have the same kind of characteristic. Anytime that you have a linear set of events, when there's complex connections between them, similar to the complex connections that we have between words in the English language, and each of those words from your domain is drawn from a relatively small set or a finite set of possibilities. This is a really nice approach to understand your data and to kind of dig in and to help you do the important part of data science, which is feature engineering, and to help you give insights directly back to the customer too, and back to the people, back to the business. So I have a little bit less than 10 minutes, look, less than 9 minutes. I'll take questions now. But if you want the code for this, it's all up on my GitHub page. There's a GitHub presentation page for me. If you have questions, email me, find me on Twitter, my website. Any questions, I'll repeat them and then answer them for the recording.
What were your next steps there once you had the findings?
So once we had the findings, actually, it was interesting. The insurance company really wanted, like, there was an actual product that was doing this kind of thing. It was just, this is weird. We couldn't afford it. It was an internal product, but we couldn't afford to go to those people, so we had to recreate it in a different way, right? So that's one of the reasons why we did this kind of thing. So the next steps were really to feed insights to other teams, but also to use these guys to build models around predicting who has certain diseases, right? That's really the key. And the reason why, here's the hook for here's why the insurance company wants to do that. They want to make sure, so the way that insurance works in the United States is when you bill, especially for the elderly, you'll cross-bill Medicare, right? You'll get some reimbursement from the government when you do certain operations and you have when people have certain diseases. But if the doctors don't code them appropriately, the insurance company can't reimburse. But what's really nice about this is, well, that's the financial reason, but the really nice thing about this is, if you build models for diseases, it catches misdiagnosis, it catches things, it catches lack of diagnoses, but it also catches people who don't necessarily know they have the disease, right? They just haven't gone to the doctor. So it's good for the patient, it's good for the insurance company, and it's good for the data scientist, because it's a fun problem. Yes?
Yeah, well, when you show your disease and your relations, the relation set, so let's say the symptoms or the other disease, they are kind of the same. So let's say they are symptoms or disease. Did you have to remodel that to filter them, or you just run the word to VEC?
Okay, so what was the pre-processing steps, essentially? Yeah. So the pre-processing steps that you generally have to do in medical data is they'll give you data that's extremely specific. Like especially for drugs, I have this drug, I have a 50 count of aspirin, right? I really want all analgesics, right? I want it to go up one domain. So that's one kind of thing you have to do. But outside of that, you really want to keep it you might want to generalize some of the data like that. Diagnoses have the same kind of thing. But beyond that, you really kind of just want to give it the data, right? It will pick out the connections fairly well, because the same thing for words, right?
But you need a classifying before. You need to run a classifier before to.
No, but this is the raw data. This is how it comes in as the codes, right? There's no classification. This is entirely unstructured. The only thing that the only thing that's being done is there's some pre-processing to make the codes more general. but that's generally like lopping off an end of like the last digit, right? Is how a lot of those codes are constructed. That's one of the nice things about medical data is they have thought a lot about building ontologies that are where you can move up in generality fairly easily. That's a common problem. But there is no classification whatsoever here. They come in as these are diagnoses, these are drugs, you know. Any other questions? Yep. Data protection. Right. So what's the data protection problems around this? So trust me, the United States has HIPAA. We have really strong data protections as well. Extreme, and it actually comes with a bite, right? One of the big insurance companies lost some what's called PHI, some patient information, and had to pay a lot of money, like a lot of money. So it's extremely important. You want to restrict access to this to the data scientists. Ah, okay. Yeah. What happens if the data scientists know that you have heart disease and you don't, right? Or what happens if the data scientists know you have something that's more embarrassing or detrimental to your career, perhaps, or something like that, and you don't? Generally, at least in the United States, I think that there are certain ways that you can do that, but I have not encountered any problem with predicting diseases, right? Mostly because the insurance company will go back to the hospital and go back. So another model that I did was looking at radiologist reports and determining if the radiologist said that the person had heart disease, right? But we never coded for heart disease. But also I looked for cancer, right? Because, you know, that seems like an important thing to know too. We had to actually have like a 911, we had to give a list to like a 911 call center for them to call these people and say, hey, you need to go to the doctor right now because the radiologist said that you have this and but you were never coded with this. We don't know if it was just ruled out exactly or if it was just dropped and communication being dropped. Which, by the way, is my pitch for data science importance in healthcare. We really should be doing these kinds of things more to ensure that those kind of things don't actually get dropped on the floor, right? There's lots of communication handoffs in medicine by humans, and that is horrendously frightening because humans are really bad at communicating with one another. Just ask my wife. All right. I have 2 minutes. One more question. Yes, sir.
After you done all of this work, do you have any particular tips for finding attribution, causation, instead of just correlation? Instead of next step?
Do you have
Recent controversy around p-values and
Yeah. So the question is, all right, I've constructed a correlation engine, but I don't get a p-value out, right? I have a cosine similarity. How do I construct that into something that a statistician won't laugh at me about? Well, so from there, if I'm interacting with statisticians, my background's in math. I actually do a lot of stats too. I like statisticians, and I like that. So generally, what will happen is I'll do a first pass filtering, and then I'll start looking individually for correlations like the R squared and stuff like that, using other statistical techniques that they'll believe, right? So think about this way: it's a first pass filtering, right? That you want to then get candidates that you look for that use other statistical techniques to find the strong connections. So, but most of the time for feature engineering, I don't have to justify it to a statistician, right? So, which is, I kind of like that world. I don't have to justify things to statisticians, but they're important to bring along board. If I'm building that into like a product, absolutely, right? You need more justification than just this is close together. Okay, I think that is it. If anyone has any questions, come up. Happy to answer them. Thanks.